Hello, everyone. We're working through an introduction to statistical methods and data analysis by Ott and Longnecker. Chapter 11, part 3, the coefficient of determination and the correlation coefficient. All right, we're going to start these lecture notes with an example from R. So suppose we have a group of students and we've measured their GPA and their SAT math scores. And what we can do first is we can ask for a summary of data $ GPA. That will give you the 5-number summary, the min, the first quartile or the 25th percentile, the median or the 50th percentile, the third quartile or the 75th percentile, and the maximum. It also gives you the mean. So in this case, X bar, where X is GPA, X bar is 2.593, and Y bar underneath that from the summary, we can see is 511.6. All right, so for our linear regression line, X bar and Y bar are guaranteed to be on the best fitting line. So we get 2.593 and 511.6. Here we go. Okay, so we get 2.593 and 511.6 will be on the best fitting line to the data. Okay, so we can use the function in R, which is LM. And if we use the generic LM, Y follows X, then that will give us a linear regression model. And so what we're doing is we're saying, let's call this object fit.1. You could have called it anything you wanted. You could have said Y, you could have said apple, you could say fit.lm. In this case, I just chose fit.1. So essentially we're just saying fit.1 gets, that's a less than and a minus sign, and then the linear model function. All right, after that, I can ask for a summary of the fit.1. And what that gives me is a lot of different things. We get the range of our residuals, the 5-number summary for our residuals. We get the coefficients. Okay, that's great because that tells us Y hat. Right? Our predicted SAT scores are equal to -77.21 plus 227.08 times GPA. So essentially here, a 1-unit increase in GPA is associated with a 227-point increase in SAT math scores on average. All right. Here, it also gives us our standard error of our coefficients. So we have beta hat 0 equals -77.21. The standard error of beta hat 0 is equal to 88.50. The test statistic T, you can double check, that's -77.21 minus 0 divided by 88.50. And that should be equal to -0.872. And then if you get the corresponding p-value where your degrees of freedom are equal to n-2, then you should get a p-value of 0.394. All right. Similarly, we could get beta hat 1, and that is equal to 227.08. The standard error of beta hat 1 is 33.24. Our t-value is 227.08. If we're testing the slope of no relationship, that's -0 over 33.24. That gives you a t-value of 6.832. And then our p-value associated with that since that's a very small number, very close to zero, it's 0.00000, 5 zeros and a 2, we can just say the p-value is less than 0.001. All right, so if we were to draw our normal curve, right, we put our hypothesized value for beta 1 in the middle. If we're testing HO, right, beta 1 equals 0, HA, beta 1 does not equal 0. We put 0 here in the middle. Then we observed a really large value for our slope of 227.08. And then we get our associated t-value of 6.832. That's our studentized value. And then we can get the area under the curve. And since it's a two-sided test, we can get that area under the curve as well. And we get a very, very small p-value. So some of the other nice things that you can see on here, besides the coefficients, are also your residual standard error, right? That's our S epsilon. And also we have a multiple R squared, okay, and an adjusted R squared. And in general, we'll use this adjusted R squared because as we input variables into the model, it will penalize you for having more and more variables in the model. So we can say here that we know that R squared is 0.7062. Then if we wanted, we could calculate the correlation, and we get that by doing the square root of 0.7062. And we know that since the slope is positive in this case, the correlation will also be positive. So we can get those values as well. This is just one example of how you can use R in a few lines of code to get these linear regression models. If you wanted to do this by hand or by calculator, it would probably be a lot more effort than, you know, a few lines of data, but this hopefully can get you started with linear regression.